Good evening or good afternoon, everyone. My name is Paraview especially, and I'm going to talk about Paraview software. This is a software that is used to do data analysis and produce visualizations for large data sets of scientific data. So normally, the kind of data that is used in Paraview is very large because it is one of the softwares that takes in large data sets without failing or crashing, and it's scientific, basically about different properties of material to try and find out how this material operates in different situations. For example, when an external force is applied to it. So in this presentation, I'm also going to talk about the datasets that come with Paraview in the examples folder. After you have installed it, we do have the discrete database, dataset, and the CAN dataset. So the first visualizations that I'm going to be trying to explain here are from the discrete dataset, and then when I reach the CAN dataset, I'll also be informing us. So from this is a contour, a visualization that was done, that was filtered with pressure, as we can see here on the legend. Here on the legend pressure, and then I use the contour filter to be able to see how deep it is, like to be able to see the different, how the data is moving from up to down. And then I also use the keep filter. As you can see here, it's clipped into half, so the image is facing the other side, but it's clipped into half. It's a full hollow cylinder. So we can see, as the legend shows, from blue to red. The blue is low. It shows a low pressure because I'm doing this according to pressure. It shows a low pressure, and the red shows a very high pressure. So as we can see here, from the outside here, the pressure is really low in this cylindrical surface. But as we go deep or in the middle of the surface, the pressure is high, and this may not really give us a lot of information. Maybe after I'm comparing it with the temperature ranges. So this shows the pressure ranges in the cylindrical. So we see here that the pressure is low on the high or open on the extreme ends of the pressure. Oh, sorry, of the cylinder. But as we go deep inside here, we can see that the pressure goes on to increase until around here where it decreases. This would also be showing the same thing that I've just showed. So here we use the wireframe. Where I analyze it with the wireframe to be able to see inside the wireframe surface. And then this is the surface that is smoother. So this shows it's a bit more visible as opposed to the wireframe. Here you can see the transitions very well. And then when we move on to this, I'm comparing the pressure and temperature distribution in the cylindrical data of the material that we do have. So you can see here that pressure, like I explained earlier, is very high in the middle here, the distribution of it, as opposed to the extreme ends where it's low. Here I use the clip filter also to clip it into half to be able to see what's happening inside of this stuff of inside of the of the material. So we can see here that the pressure is very high in the middle here, as opposed to the extremes, and it goes on to be high. And we see temperature varying in a different manner. It's high only at mostly the center and not so much on the outside of the data. And for the pressure to be like this, it can also be attributed maybe to the density of the air in this cylinder. Because as the air keeps pushing down on it, then the high chances that the pressure would be high. And then yes, I also further analyzed it using the streamlines filter, the glyph filter, and also the tube filter. So the streamlines filter helps us to see the streams on how this on how I'm using temperature, on how temperature I query the data according to temperature, on how temperature is moving in the data. So we can see that its concentration, and we can see from this that it's moving onto the downward direction, like the air or the wind is moving onto the downward direction, and temperature, like we saw here, it's concentrated more at the core, and here the core is really the bottom part of this. So the streamline shows these streams, and then the tube filter helps us to make the streams look to be more visible, so that we can be able to see where exactly they are passing. And then the glyph filter helps us to show the direction of airflow, and to also help us understand where so much that the pressure, the temperature is high. So from this we can see that the airflow is really coming from up and down, and it's mostly concentrated here, and it's sort of moving away from the bottom is not really seen here, but it's moving away from the center, so it's not so much concentrated at the center, but the temperature is high at the center. So this is, I went further to generate the line graph. This is basically pressure and temperature, and also a histogram, and it was also temperature. From this, from the previous image that we have of temperature, I did generate a line graph to show the distribution of temperature and pressure at different points. We can see that pressure is a sort of a bit not so, it's constant at different stages of distribution. Like we can see here, the pressure is high, but it's constant. And then for the temperature distribution, it keeps it's very high at this point in the distribution at 1,000, and then it goes on reducing, and then it also sort of stabilizes, like it's constant at this point in the distribution. The pressure distribution is constant in the image. I think that would be the highest here, and then here, and then the lowest, we go on reducing it down as per the line that I drew on the image, on this image. And then for the histogram, we are seeing different 300, how many 300 temperature points are given, distribution of around 0 to 6,500, and we can see them, they are around, for the 400, they're around maybe 800, the 800 distribution there. 400, the temperature to be at 400, around 800 distributions in the data, as we see and go on, as this is actually reflecting. I'm sorry, I'm really having flu. And then we go to temperature. This is the distribution against volume. Trying now here, coloring it instead of I'm coloring it in the surface instead of having, a clean surface wireframe, I'm using volume to see the volume of the temperature at different distributions, and we can still see that it's still high at the same point. There is not really much that has changed. Then for this, this is where we move on to the discrete data set. In the discrete data set, measuring this against EQPS, which is basically showing the rate at which this this is the CAN, not discrete. Yes, the CAN data set. I'm measuring it against the EQPS to see the rate of decomposition of EQPS is basically a value measure of the rate of decomposition of the plastic in the material. So we can see here it doesn't really decompose a lot, or it doesn't really get destroyed easily, because in a short period of time we can see this is a line graph showing the distribution. We can see that at this point, this is time. We can see that at this point in time, it's sort of reduced. At this time, it was reducing gradually, not so increasing gradually, and at some point it was really constant. So we could say it doesn't get destroyed in a very at a very fast rate, or that the rate at which it gets destroyed is constant. So this is helpful in determining what kind of plastic that you want to use when maybe packaging different materials, or if it's going to be used for construction. How strong is it, and how strong is it? What kind of force or amount of force can it withstand, and at what time does this break down? Yeah, so this is why this is important to know. It's the rate at which the plastic composition, this plastic will decompose, to know how much pressure you can actually exert onto it before it gets destroyed completely, as we can see here. And then this so this graph was really basically about this cut section here. I used the extract surface filter to be able to extract this section and then label it with EQPS, so that I can be able to generate the average here, which is this here, as I'm trying to explain. Sorry about the figures are not so visible, but we can see from the legend how it ranges, and we can see, I would think this doesn't really decompose very fast, and it doesn't, like, it's a strong type of plastic, because in the middle here where it's just red, it shows like it's highest, but it's a very small section as opposed to the rest of the sections that are that are blue. So it could be a good plastic for someone who wants something really strong. And then yeah, this is also sorry, I wasn't able to add the video showing the crashing of the data on different variables. Like, this is what I've just explained on the EQPS. So we can say it's just this cut section that is, maybe I would say, very weak, and it decomposed. It got destroyed completely, but the rest is fine. But this is displacement magnitude. Displacement also is like how much force can get this plastic out of its original position. And they both took this little time to be able to produce this image here. And we can see that for displacement, it's really a very big amount that gets really displaced, given a very huge force in a very small period of time. So you would want to rethink if this works for you or not, or if you want to, depending on the type of or the use that you want this to be used for, you would want to rethink if this works for you or not, or to get something that is not easily displaced from its original position. So from this, I was trying to show the different positions, because I also use the temporal filter, and for it basically showing how this data crashes smoothly through, as opposed to the original one. But yeah, the video wasn't really able to upload, but I hope I've given some insights into it. Yes, so these are the images. I sort of saved the video but got images, but yeah, these are the images showing for EQPS, and this basically this first section without the temporal filter, and this with the temporal filter. But of course they do reach the bottom line in the same period of time, though this the crashing of this is way smoother as opposed to this one that is like rigid, more with timestamps that you can see, and this is way smoother, though they were both in the real time setting instead of that timestamp. I hope I give some insights into what this data is. So in conclusion, I'd say Paraview is really a good tool because of, one, its capability of taking in large data sets and without crashing, and it's able to analyze scientific data that was really needed to be used. Thank you for listening.